Hi, in this video I will talk about TP6841S6A, synchronous buck converter, step-down converter. Before we can build a circuit, we need to understand our main components. So we are looking at the data sheet for this type of buck converter. You have to think about the data sheet as an official rule books. So you have to follow everything exactly how they describe to have the best result. Just note some data sheet, as I said, they really explain things well and they have really good data sheet. This one is a really short data sheet and there are not much, they don't explain a lot of things. So the reason to pick up this to show you how to even manage if you have not so well data sheet to manage how to do your work. So first page, you can see they have a general description. What is this buck converter? The input range, it's from 4.5 to 40 volt. Then it can drive 800 milliamp. So if you have a load required more than 800 milliamp, this will not work for you. Then it has two integrated MOSFET. So that's mean it's a synchronized because in synchronized buck converter there are two MOSFETs, and unsynchronized buck converter there is one MOSFET, and then we have a diode. So they claim also the efficiency it is up to 95%. Then reference voltage. So this the voltage you calculate your output using voltage divider as we saw in the LDO as well. And it has excellent line and load transit response. So this when your when your current suddenly change, how it will affect the voltage drop and how fast will recover. So they said it's stable with ESR ceramic capacitor. So similar also to the most of the LDO. It has some feature, short circuit protection, terminal shutdown. So when the IC got hot, then it will just shut down instead of getting damaged. Then they have the range for temperature range, same of what we talk about the LDO. They specify the package, this package. And they always, in most datasheet, they just put you the typical application of the datasheet. So you can use this, but also it depends on your VN and Vout. But it show you it's required, for example, two capacitor in the input and one capacitor in the output, and then it require the feedback here, two resistor R1, R2, and the inductor and this C2. So if you have a different application, the capacitors will stay the same amount and the inductor will stay here, but the values can be changed depends on the calculation. Next, you can see the pin configuration. So they describe each pin of the buck converter. So it has 6 pins, as we say here. And so first pin is the PST, boot start. So this pin help to drive internal high side MOSFET, and it's require a small capacitor with 100 nanofarad connected between this pin and the SW pin. Then we have the ground, the feedback, we know what is it. Enable pin, so you have option to enable and disable your output of the buck converter. Then Vn is the main power supply. So they recommend bypass with 22 microfarad ceramic capacitor. And you can see later they should write more specification about this capacitor as well. Then you have the switch node, so the output of the internal switch. So this is the heart of the converter where the voltage swing repeatedly. And the inductor connected between this pin and the output pin. Next, we have the absolute maximum rating. So that's exactly similar to what we talk in the LDO, the OGA, GC, and the power distribution for this package. So they don't have different packages. As we saw in the LDO, the IC come with different packages, but this one just have one package. Next, what you have to look into is the electrical characteristics. So they telling you different parameters. First, the Vn. So this is the maximum voltage on the Vn that the buck converter can accept. So it accepts 4.5 to 40. Just a small note. So they wrote here that battery power system. So you have to really be careful because if you're using one lithium battery, the voltage is 4.2 and it will not work with this buck converter. So normally they just put it as a commercial uh, and they could argue that, okay, you can connect two batteries, then you will have like 12 volt, for example, with two batteries, and then you can use it. But for single cell, it will not really work. But if your battery more than 4.5, then it will work. So we back here. We have Vn under voltage protected. Typical value is 4.3 volt. So that's mean this regulator, if the voltage drop below this value, it will shut down since it has a protection circuit. So it will just shut down if it goes below 4.3 volt. Then this FE voltage, so this is the feedback. Our reference is 0.8 volt. I always use those typical values instead of the main and the max. And this is the switching frequency, so it's 800 kilohertz. So the fixed speed of the internal switch. So this is the key input for your inductor and capacitor calculation. And then you have the duty cycle, you have the maximum on time. So this is for the MOSFET on time when it's open. And high side switch resistant, RDC on high. So the resistance of the MOSFET is 450 and in the low side is 270. So those all also you need when you do your calculation. That's mostly what is important here. Then here they show you the block diagram, how they implement this buck converter. Here they just show some example about efficiency in different cases. So in case of Vn 12 volt, then we have different voltages with different efficiency, and this is the load current. So you can see here in, for example, 200 milliamp, the efficiency is almost 93. And then if you have a VN 36 volt, the efficiency is around 80%. Here they just make some test how this buck converter will behave in specific voltages, and Vn is 12 and Vout is 5 volt, and then the load current is 800 milliamp. And this is very important also to look on. So this is all the function description. So you can read it, you have to read it carefully one by one. And here they specify some application information. So this is to set up your output voltage. So if you need, for example, 3.3, you can use R2 24 kilo ohm and R1 75 kilo ohm. So most of the good data sheet as well, they provide all this information. And also they provide you all formulas you need in your calculation. So the inductor selection, for example, it can be ranged between 4.7 to 22. So that depends on your input and output voltage that you make the calculation based on. Then you will see which value you will get, and you have to implement this value in your schematic. And notice what they said, the inductor with DC current rating of at least 20% higher than the maximum load is recommended for most application. Then if you need higher efficiency, then the inductor DC resistance should be less than 15. And here the equation how to calculate the inductor, and the ripple current delta L delta IL is approximately can be 30%. Also, they put how to calculate the input capacitor or what to use as an input capacitor. So that's what they recommend. So you need also to read that. So basically, it's ceramic capacitor with X5R or X7R and low ESR, and then they put you a typical value. So basically, you can trust this if it's a good company. Then you can immediately use 22 micro and then use 0.1 micro or 100 nanofarad in the input. And the output, so they put a calculation. This is also depends on your output voltage compared to the input voltage. So you can use this formula and then you can calculate your output capacitor. But since they said also it's for most application 22 micro farad, it works for everything. You can just be sure of this calculation and see how it will affect your application. So this is the most important thing you have to look in the data sheet, and they put you some reference as well. So if you have voltage from 5 volt to 40 and V out 3.3, so you can see when those numbers change, the inductor value change, and the C in didn't change at all, and C out didn't change, and here even when reference to the Vn changed, the inductor value just changed, and then the rest are still the same. So that's tell me I don't really need to calculate the capacitor value because it looks they tested for those values and it can work for the all Vn range and V out range and the I out current, which is from 0 to 800 milliamp. So that just the inductor value is always changing. Here is the package, the dimension. So here, if the packages not exist, you can make it an Altium, and that's it about reading the datasheet. So this is really simple datasheet. Uh, More companies like Texas Instrument or MPS, they have more details, and on this buck converter, it can have a lot of functions, so you will see a bigger datasheet. Thanks.